Good time of the day, everyone. This is Ivan from EPIC, and today you're watching the EPIC online technology meeting on LIDARs on chips, one of the series of our online technology meetings on all the aspects of photonics, presented to you by EPIC. EPIC is the European Photonic Industry Consortium that unites 800 companies from all around Europe, from all the values of the value chain. And let me remind you that EPIC is there to support you with the technology consulting, market studies, networking, marketing, mentorship assistance, assistant with recruiting, and with investment. Today's event includes 7 exciting talks from the key players of the LIDAR market. We'll start with a presentation by Marelli Automotive and CEA-Leti, followed up by Viavi Solutions and Ommatidia LIDAR. We'll also hear the presentation of VoxelSensors, DeepLight, Outsight AI, and the VPI Photonics. And with this, without further delay, I would like to present to you our first speaker, who is Frédéric Chave, the Director of Business Development and Product Management for ADAS systems at Marelli Automotive. And I will do the joint presentation with Thierry Mourier, the integration assembly engineer from CEA-Leti. Both of them together, they work on a LIDAR project called Tinker that enables the 3D integration and advanced packaging for the next LIDAR generations for autonomous vehicle driving. So, Frédéric, whenever you're ready, welcome to the EPIC Online.
Hello, everyone. And so I will be co-presenting with Thierry. We are working together since several years now on a project called Tinker. And this is a European project. Maybe you're sharing the wrong screen. Here we go. So the Tinker project has been started around 3 years ago now. We had last week our 3 years meeting for Tinker, and we have been working together. So with Leti, I'm part of Marelli Automotive lighting branch, and I'm caring for the integration into lamps and grilles for sensors. I'm Frédéric Chave. So you can maybe go to the next slide, Thierry. Here is just a short presentation of all the players and partners in this exciting project. The project focuses on both the radar and the LIDAR. So there are 2 main groups within this team, but we are both working all together into the, let's say, focus for fabrication using nano imprint lithography to make more compact, cheaper, and faster production solutions for sensors. And you can check out the website as well for this European Grand project. So the combination for LIDAR goes first on the optical phase array LIDAR demonstrator that Thierry will detail afterwards. And this is focusing on nano imprint lithography, as I mentioned, and through silicon vias, which is well suited for higher number of in and outs and a faster production time, as I mentioned earlier. What we're seeking on Marelli's side is a more compact LIDAR technology that we can more easily integrate into automotive space, being lighting, for instance. Here I just extracted some numbers from IHS and Pores just to show the development of business LIDAR in the next 10 years. So on the left side, we see definitely a predominance of the demand for LIDAR in the Chinese market. But what's interesting below that is also to split into the locations of the LIDAR sensors on the car. And as you can see, right now it's a bit of a mix, but let's say within 5 years, we see a clear trend at the front and front corner. So when we say front, it's on the grille side, and front corner, which would be either on the grid corners or above on the lighting structure. That's where we see most of the demand for LIDAR, while at the same time, demand for roof application is quite stable, coming to a plateau around 2026 and not moving above the 1 million pieces a year. French. So overall this push also for what we are the motivation of being part of Tinker is to support for future integration for more styling approach versus maybe what we see today, LIDARs that are protruding on the side of the car or on the top of the car. Future application, as we see on this Toyota car, would be much more integrated and even non-visible to the end user. So with that, there is also a growing need of sensor. This is quite classic information. 10 years ago, we had only 6 sensors on the car. Maybe 10 years from now, we will have 5 to 6 more count of sensors on the car. Just even current cars have around 20 sensors. So what it means is that we need more space to fit all these sensors on the cars. And with that, we are promoting the integration, what we call smart corner. So for the next slide, Thierry. Yeah, here the smart corner solution is not only on the lamps, it's also the integration into panels, as I mentioned, but also on the rear lamps. Why not? For radar, LIDAR cameras, which would be visible camera or infrared-based camera, and also communication solution for V2X application, microphones, Li-Fi emitters. And on the other end, the source of light could also support better performance of some sensors when we are integrating infrared illumination or specific illumination that are working in coordination with front view cameras, for instance. So on the LIDAR locations, there are a lot of talks about where we could have the best position for sensors, and especially for LIDAR. We see most of the application today ending up on the roof or just on the front part of the roof for the more novel cars. But we are always facing blind spots and dead zones on the front or on the sides of the car, and this is definitely an issue for most of the application where you want to have a greater operating domain, being, for instance, urban areas. And then, of course, there are some complex occlusion to care for when you have difficulties to be very close to some objects. I'm talking here about mirrors or even glass windows, which are extremely difficult to detect with a LIDAR, or very thin pillars. So it's valuable sometimes to bring the sensors a little bit down, and you lose on one side from the sight point of view, but you can gain for the blind spot. So yeah, what we see here are a lot of different challenges, cost being for sure the greatest one currently. As I mentioned earlier, we are trying to find more compact solutions for size and form factor to be able to fit these LIDARs into equipment. Then we are always trying to mitigate for weather impact. Putting a LIDAR on the roof is an extremely hot space to remain. So we also try to find solution to be able to clean better the sensors, having maybe less mud, less impact of fog, which are inside the equipment. I'm not mentioning about the fog outside. And then, of course, having a cleaning system that can be embedded into the equipment is easier. Having shorter lines of cleaning to reduce the cost, and integration in the car facilitation is also a key. I will not list all of these items, but overall, what is important for us in the last 3 items are also the impact of putting outer lens in front of LIDAR, as of course we are impacting on the reflection, and we are also deflecting the beams as well as distorting the beams. Yeah, for the next slide, just to stay a bit on the time, just a few summarize of the key advantage of the smart corner. We are talking about environmental protection, as the sensor is embedded into a much robust item like a lens of a headlamp. We can have the cleaning system, which are already available in this area in action. We can embed heating systems as well to extend the operation of the systems, even in very cold weather. We can reduce the wiring, simplify the harness, and of course the cost and the weight, not to mention. We can also embed some leveling system. We have a much greater field of view, as we will see in the next slide. And then obviously the aesthetical part of it is fundamental for the end user. So when it comes to the field of view benefits, putting sensors into lamps and on the corners of the car is also of great interest when it comes to crossing. For instance, you have a predominance of the car front in some corners that maybe would be occluded otherwise when you are looking from the windshield or top of the roof. that's also valid when you are exiting a car park, for instance. And to the right side, another application, when you have occlusion from a front object, preceding car, for instance, you may not be able to always see a pedestrian or an object on adjacent lanes, while putting the sensors on the corners of the car will give you an advantage and faster detection. So, of course, this has some limits, and one of them being that you still have some blind spots on the sides or some cone of occlusion on the front of the car. But again, this can combine with a greater number of LIDAR when it comes to a cheaper solution, like we hope Tinker will be able to provide to us. So this is, I think, the last slide on my hand. Thank you very much, and I give the stage to Thierry. Thank you.
Thank you, Frédéric. So I'm going to move to the second part of this presentation, considering the process developments of the Tinker. So just a few words about LIDAR first. So let's say LIDAR is part of the CEA, which is the nuclear agency in France. So we are 2,000 people working on Grenoble site with a lot of patents and 68 startups created for 20 years now. And we are working on 200 and 300 millimeter wafers in a 10,000 square meter clean rooms. By myself, I'm part of the Photonic divisions on which we are developing technologies for images, silicon and photonics, displays, optical sensor, and so on. And in this division, we are focused on high-performance technologies. You can see some of the topics on which we are developing our technologies. And for that, we need the photonics packaging, and I'm part of the photonic laboratory on which we develop all the packaging items that are required to integrate fully the chips to get from the device to the complete system. So it includes the fine pitch interconnects, the photonic interposers that I'm going to talk about. Okay, so what's the Tinker project LIDAR motivation? So the motivation, of course, is to move to the next generation of LIDAR, to remove the limitations brought by the mechanical steering that is huge, slow, and expensive. And for that, first phase of the work carried out in LIDAR was done to bring silicon wafer level technologies based on the OPA, the optical phase array system. So you can see some of the features. I will talk more after. So it's a silicon-based technology, including the photonics, but also all the technology to make the beam steering, and also to provide all the connections to the different channels that are required for the LiDARs. So this is something that works. We have proven that for quite a years. But if you look at what can be extracted from that and can be packaged, then you can see that there's a lot of wires, too many wires. This is only a 256 channel OPA, but we know that the autonomous driving will require more than 1,000 channels, which is much more than what can achieve the classical wire bonding. So for that, Tinker was designed, and the goal in LIDAR was to bring new 3D integration and packaging solution to make the full integration of the photonic IC on an interposer. So this passed through the realization of an interposer that will contain the OPA, but also all the CMOS drivers and at least the laser. And to be able to connect the photonic circuit on the interposer, then there's a need to bring the connection between the front and the back side. And this is made using TSVs. And initially, this was based on a mid-process TSVs of 10 micron diameter. And you can see a picture of this large feature. And to be able to connect everything, then let's say a fine pitch, high density flip chip was enabled. So to go through the processing, then the first phase is to make the photonic processing, and the goal was to have everything ready and working with the conventional silicon oxide technology. So you can see here the definition of the grading couplers to bring the light in, and also the waveguides and the splitters. Everything is made using silicon and silicon oxide. Which means that this is a standard technology on a standard silicon technology platform. Then moving to the beam shift, then the beam shift is ensured by the use of a thermal heaters by a simple resistance made of tinitride, and then there's conventional tungsten contact and aluminum copper metallization. So all these photonic parts is completely standard with standard silicon technology platform. However, to do the complete integration, we brought the TSV technology to be able to connect the two sides of the circuits. So there's two types of TSV available and developed. So the option one chosen in Tinker was the mid-process TSV, which is performed between the contacts and the front-side metallization. It enables for high density, high performance, and small footprint. But as the wafer is thin that to 100 micron, this lead to a die warpage that is quite pretty complicated flip chip. It's to notice that this mid-process TSV is typically available in IDMs and foundries. On the other hand, to increase let's say the easiness of the flip chip, then you can think about doing the TSV at the end of the process. It's called TSV last. So in this case, the TSV is processed on a finished, I would say, device. This leads to a thicker silicon to reduce the die warpage and easier processing steps. However, in this case, of course, there's a loss in the density because TSVs are larger, so a larger footprint. And this is typically TSV that are available in OSATs and foundries. So both are developed in Tinker in order to propose the two solutions for a product to be either transferred to IDMs and foundries or in OSATs. So let's take a few words about the different technologies. So the mid-process TSV, so it's a TSV of 10 micron diameter, and that is fully filled with copper. So you can see a picture of the TSV, which is 100 micron deep and 10 micron large. Followed by the metallization, and after the metallization, then you just flip the wafer, you bond it on a carrier to go back and take the contact on the backside. Realize let's say the metal routing on the backside, and finish by performing the copper bumps that will lead to enable the flip chip technology. So that's the first way to do the TSV. The second one is the TSV last. This is a development that is clearly in progress now. It started later in the Tinker. So in this case, you get the circuit to the end, then you flip the circuit and bond it to a temporary carrier, and then you grind the silicon to reduce the thickness to the thickness that you want, typically in the range of 200 to 300 micron, and you do the TSV, etching the silicon, going to contact the metal, the upper left metal level of the circuit. Then you do a copper lining that you can see on the right part below. Because it's complicated to completely fill this type of features, and at the end, you do the copper burns, and you enable. You just have to debond the wafer, and then you enable the flip chip possibilities. Concerning flip chip, both thermocompression and mass reflow are the typical technologies that you can find. So thermocompression is very robust for R&D, and mass reflow is something that is much more dedicated to manufacturing because it's fast. So in Tinker, we both use the two technologies to be able to move from the R&D towards something that is transferable to manufacturing. Here is some example of what have been done using mid-process TSV. So you can see here the top. Oh, sorry. You can see here on the screen the bonding of the OPA on a silicon substrate on the interposer. This is something that is working well. However, we face some severe wafer and die warpage, typically warpage in the range of 200 micron, which is perfect for R&D, but seems to be quite complicated to transfer to to manufacturing. However, this is we enable the possibility to flip chip the OPA on 200 millimeter wafer using the die to wafer techniques, and you can see typically results of the thin OPA, the TSVs, and the flip chip areas with the contact between the let's say the steering LiDAR and the interposer through this flip chip. So to conclude my talk, I would say that the Tinker LiDAR platform proposes to anyone a photonics 3D integration packaging solution to meet the LiDAR requirement for ADAS. So photonic on silicon, TSV, and fine pitch flip chip are integrated. And we are in the final phase of the testing phase today and integration. So the technologies proposed on CEA-Leti silicon platform through the Tinker project, and of course the participation to the EPIC technologies today is allows Tinker consortium to disseminate the work carried out in this European project. That's for me. Thank you for your attention.
Okay, thank you, Thierry. Thank you, Frédéric. Very interesting presentation, and congratulations with mounting up such a complicated project together with so many partners.
Yeah.
I'm curious, maybe you can answer our most important EPIC question. So it's more or less clear what you offer to the community, even though you can still highlight this, but also what the other members of the European photonics community could do for you to develop this project further.
Frédéric, do you want to start?
Well, first, to continue the dissemination, I think this is one of our requests here. This is, again, a public project, so available to continue its life through different ends. And one of the purpose here is to let the community know about this technology. The fact that it was also developed for an automotive context, which is also new for the OPA. Yeah, that's what we've been working now for some long time. So here it is.
I would add also that solid state LiDARs are now in the phase of moving up to and ramping up. However, it's still confidential. It's a technology that is new and has to be shared in order that everyone knows where are the progress, and then we can disseminate and spread this technology to have more volume for it to be interesting in terms of integration and costs.
Okay. But so you say it's available on the Photonics platform of CEA-Leti, but what's the future of the commercialization of this?
In fact, there's two parts. So the OPA is being developed using the optical phase array, but there are other ways to do the steering, other techniques, part of the thermal shifting to do the beam steering. However, the packaging phase, the TSV and the packaging are compatible with all the techniques that you can add for photonics part. So today we are developing the complete process to move from the typical silicon photonic on silicon device process toward the complete system. integrating all the packaging phase and reducing the LiDAR size.
All right.
You can come and see the demonstrator in March. We are exhibiting this in the LOPEC in Munich in March 2024.
Okay, sounds good. So yeah, I'm now going to open it for the questions from the audience. So please feel free to ask your question. Just push the raise hand button at the bottom of your screen so that I can pass you the board. In the meantime, I already see in the chat we have a question from Eric Mazalera from ST Microelectronics. Yeah, Eric, please go ahead.
Yes, I understood in the introduction of your project that nano imprint was one of the key technology for this project, but I did not catch the use of it in both presentation from Marelli and CEA. Can you explain?
Yeah, maybe I can give a few words. In fact, this is a parallel work that is done with the nano imprint technology. The goal is to use the additive technology to reduce the cost of the silicon. So typically for the generation of the waveguides, we use standard let's say lithography etch multiple step process to do these waveguides. And the goal of the Tinker project was also to study in parallel to the standard way additional nano imprint and inject technologies to do the waveguides by only let's say a multi-steps print of the waveguide in a let's say high refractive index polymer, and filling that with another polymer by inject to generate the waveguide this way. Okay, does it answer to your question?
Yes, thanks. That's clear.
All right. Okay, thanks, Eric. Now, Carol from Photon Delta, please.
Yes, thank you. Thanks for the interesting presentation. I saw that you steer the OPA with thermal elements. However, you say also you need many channels. Is that compatible with the power consumption and the crosstalk, etc. in the future?
Let's say the power consumption is supposed to be around 10 milliwatts per channel. So for the 256 channel, we are in the range of 20 watts. So it's these are the targets, yeah. But if we increase the number of channels, of course the power will increase a bit.
Okay, thanks, Carol. Now, Lionel from Traction. Please unmute. And,
Hi, so this is Lionel from Traction. What is the kind of resolution that you can achieve with your OPA, and how do you manage the side lobe that we can get with an OPA?
Okay, the resolution is 0.2 degree per channel typically. So for we have a plus minus 20 degree range. And to manage the second part of your question was
about the side lobes that we can get with an OPA. We have the principal beam, you know,
yeah.
and like with optical antenna, and you have side lobes around this principal beam, and in general it's around 12 dB. The first side lobe is around 12 dB, the first lobe. So how can you manage that with your OPA?
I'm sorry, I'm not a typical optical guy, so I don't I don't have this number in mind. So
okay, no
sorry.
Problem. no problem. Thanks.
Okay, no, but feel free to follow up after this meeting also.
Yeah.
For details, yeah, Lionel, you're welcome to contact Thierry or me, and then I put you in contact.
Okay, thank you very much.
Sorry.
Yeah. You're welcome. Anyone else? Because if we don't have further questions, okay, there's one more. Mansoon, please.
Hello, Dr. Thierry, and thank you so much for the talk. I would like to know, how do you fill metals with a trench or a hole with few micrometer deep? What technique do you use exactly for it?
Oh, so the metal filling is done by electroplating.
Oh, does it affect the resolution or any other, shape and size? Because metal electroplating has some other effects on the shape and size when you do precisely.
Yes, so that's a key for the you mean for the TSVs, for example?
Yeah.
Yeah. So typically that's the one of the limitation of the mid-process TSV. We are limited to some aspect ratio around 10:1. So let's say the ratio between the thickness of the silicon and the diameter of the TSV will be fixed by this limitation.
Oh, okay.
But
Thank you so much.
Work to 10:1.
Oh, thank you so much.
You're welcome.
Okay, yeah. So thank you for sharing so many details, and yeah, it was very curious to see the outcome of this project. So we thank our speakers again, and I suggest we move to the next presentation, which is given by Scott Rowlands, the Senior Product Line Manager for Automotive Sensing at the famous Viavi Solutions. So Scott, whenever you're ready, the floor is yours.
Okay, can you hear me?
Yes.
Okay, great. Well, it's my pleasure to be here at EPIC and present this talk to you. I represent Viavi, and Viavi has been in the optical filter business for 75 years now. So we're an established company with a worldwide presence. And today I'd like to present to you our filter technology. And the key is enhancing the sensor performance. And hopefully this can give us a little glimpse of how LiDAR performance can be improved and where it can be improved more in the future. The main point is attention to detail and applying this latest technology for optical interference filters. So should be familiar to most people that the key components are shown here in the slide. And the main emphasis of my talk today is looking at these components. And the light source, of course, is where it starts. And that has several areas that really must be understood, depending on the type of source. It has the wavelength, the manufacturing tolerance, the temperature shift. All of these things need to be included in your analysis. The lens system is the next key factor, and this determines the angle of light in the system. For my discussion today, I'm going to focus mostly on the filter in the system. And the filter in the system is where sometimes can be the most least expensive component, but its design and performance can really have significant implications on the sensor signal-to-noise performance. And so let's jump into that. The first thing I want to talk about as a key technology in filter technology is hydrogenated silicon. And at Viavi, we developed this and have extensive coverage for this, patent coverage for this. And the key contribution to hydrogenated silicon is that when hydrogen is properly incorporated into an amorphous silicon film, the range of transmission moves all the way down just above the visible spectrum. And without the hydrogen, amorphous silicon is really not useful in the near infrared, even up to 1550. Filters in LiDAR systems are typically based on alternating layers of low and high refractive index layers to create interference and filter the light appropriately. Hydrogenated silicon, when used as the high index material, has two main benefits. The high index, first of all, it enables a lower cost. And the second one is it reduces the blue shift for light rays at increasing angles of incidence. For an interference filter, a filter at light ray like this blue line here at 0 degrees will be the most upscaled for center wavelength for a bandpass kind of filter. For an interference filter, when the light rays come out at a higher angle of incidence, like this red line here, then the filter will shift towards the blue spectrum. It'll shift down in wavelength. And there's an equation here that describes this effect. And again, we're talking about, what was the advancement of hydrogenated silicon? Well, this index here, N effective index, is highly dependent on the materials in the design, and this high index material of 3.5 to 3.7 really changes the game for this. So let me show you some examples. So here is an example of a narrow bandpass filter, and we plotted it here in wavelength, and on the x-axis, the y-axis transmission. And what you see here are two identical designs. Well, no, not identical because they have different materials, but identical performance. And you can see the traditional bandpass here represented by the red dots. That would be a bandpass that's constructed out of previously oxide materials such as titanium dioxide and SiO2. And then overlaid on top of that is a design with hydrogenated silicon and SiO2. And you can see the performance here is identical. What you want to look at on this table here is in the traditional design with an oxide of like titanium as the high index, titanium dioxide. It takes 52 layers to achieve this design, and the coating thickness is 8.2 microns, whereas the hydrogenated silicon is only 28 layers and a coating thickness of 3.2 microns. So what does this represent? Cost of this product is really a function of the layers and the thickness. And so the first benefit that we see by incorporating hydrogenated silicon into this design is a lower cost with the same performance. And for LiDAR systems to reach mass production, especially in passenger automobiles, cost and performance are going to be key. And so this here enables a lower cost. And as I'd like to explain on this next slide, it also increases the performance, less blue shift. So now transitioning to this slide, this is the same example earlier. And what we're looking at now is that angle shift that we talked about earlier, the blue shift. And in this slide, looking at an angle of incidence or a light ray shift of 20 degrees, you can see that the filter has shifted downscale, and that traditional red dotted filter with titanium dioxide SiO2, the blue shift is 13 nanometers to the left. That'd be the solid green line here. And so that gives you your usable bandwidth over that field of view on the returning light into your system of 17 nanometers. And so the filter bandwidth, in order to accommodate just that shift, not the temperature shifts, not any of the manufacturing tolerances, we're only looking at the angle shift. You need a bandwidth of your filter of at least 49 nanometers to have a 17 nanometer usable bandwidth. And that 17 nanometers can then accommodate those other factors of manufacturing tolerance and temperature shift. If we look at hydrogenated silicon, because of the higher index, and with that formula we looked at, the blue shift is only 5 nanometers. So that means that we only need 41 nanometers of bandwidth. And we still have 25 nanometers of usable. However, that means that we can also reduce this bandwidth even more. And bandwidth in the near infrared here is one of the key performance factors in improving your signal to noise ratio. So this is a dramatic effect of the hydrogenated silicon. And I think I can comfortably say with our position in the marketplace that this is the dominant technology now for filtering light for systems that need light filtering in the near infrared. And so that's the first consideration, is considering all of these factors. And again, we didn't go into optimizing and matching the temperature shifts and manufacturing tolerances. So, but if you want still greater performance, and this is where the technology is headed today. In the past several years, we've really seen mostly first generation LiDAR systems built. And we're moving now into second generation systems, and the cost and performance is becoming even more critical. And what I want to demonstrate here is one other concept, and as my last concept here. And that is that we need to even have narrower bandwidths for better signal to noise, and without adding a lot of cost. And the solution that I'd like to present here is binning filters and lasers and matching their center wavelengths, and thereby improving our manufacturing tolerances. So the first example, and we're going back again to that same filter that I showed earlier. And if you're looking at a laser spec, so let's say a typical edge-emitting laser or even a VCSEL, they might have a manufacturing tolerance of plus or minus 6 nanometers at 905. And so if you're designing a filter, you have to, first of all, you have to make sure that the bandwidth can at least cover the laser light. And so that'd be 12 nanometers to meet that manufacturing spec from your laser manufacturer. And then filter manufacturers also have a manufacturing tolerance. We can't build filters exactly on wavelength in high volume with this kind of precision. We can do about plus or minus 4 nanometers, sometimes even better. It depends on what your needs are. But in this example, 4 nanometers, plus or minus 4 nanometers, requires 8 nanometers of filter bandwidth. So you add these two up just to match manufacturing tolerances. Okay, earlier we talked about angle tolerances. Now we're talking about manufacturing tolerances. And here you need 20 nanometers. So here's the example of how you can reduce this. If we can work with the laser manufacturers, and they can sort and bin their lasers in plus or minus 2 nanometer bins, they can still use their entire production plus or minus 6 nanometers. However, these are now put into 4 nanometer bins. Okay, and then we as Viavi, your filter manufacturer, we can match our entire production and put it into 2 nanometer bins. And so the total bandwidth now required is only 8 nanometers. That's 60% narrower than the previous example without binning. This is a dramatic improvement in sensor performance. And in fact, we see this as the trend that LiDAR manufacturers are considering today. Now, does this cost more? It does cost a little bit more, but it's very manageable. We have automated our filter production methods to do this sorting. And it's, again, I would say it's the #1 growing feature that LiDAR manufacturers are looking for today, is this kind of performance. And we've worked hard to keep the cost very under control. And so with that, I just want to encourage you that as you're looking at LiDAR performance, really optimizing all of these systems together is the way to do that. And there are advancements being made by the laser manufacturers, the light shaping and lens manufacturers, and on our end, the filter manufacturing. And so we continue to look for ways to improve performance. And I hope this has been helpful in understanding this part of a LiDAR system. So I'm open for questions.
Thank you, Scott. Yeah, this is indeed a very important part of any LiDAR system. So please, yeah, go ahead with your questions. Now, Olaf from Eclipse Optics.
Hello, Scott. Thank you for this presentation. Just wondering, is there any difference in like temperature performance of the hydrogen silicon or other like environmental factors?
Okay, that's
like
a great question. The hydrogenated silicon does have a higher shift with temperature. It's about 0.07 nanometers per degree centigrade at this wavelength I've shown in the 900 nanometer range. That actually is almost identical to a VCSEL temperature shift at that wavelength range. And so if you're using VCSELs, that the match there can be very helpful in reducing that. An edge emitting laser has, I think it's much, much higher than that. I think it's close to 0.3 nanometers per degree centigrade. And so that is one consideration. If you're building an extremely narrow system with, let's say, 1% bandwidth, such as 10 nanometers, 8 nanometers wide, then that temperature shift could be problematic. And then you would be forced to go back to the traditional materials such as titanium or niobium pentoxide. Those materials have almost an order of magnitude lower temperature shift, and those would be more temperature stable. So it really depends on optimizing your system. Is temperature more important, or that blue angle shift more important? Once you get over, in our experience, about 15 degrees of field of view coming into the filter itself, the angle shift becomes more important. That's kind of a crossover.
Okay, interesting.
All right. Anyone else? Okay, Mansoor.
Dr. Scott, thank you so much for the talk. But I'm wondering, would this can be integrated with VCSELs directly on top of emitter? Can we just deposit silicon, hydrogen, the layers, whatever you say, or we need a separate setup for it?
No, in fact, we do deposit these kinds of bandpass coatings directly onto sensor wafers. We use a photolithography process, and we can deposit it with fairly low temperatures onto a sensor wafer, and thereby do that. If it's backside illuminated, we don't need even photolithography. We can just put it straight on.
Okay. Do you think there would be some kind of interference between the contacts and the deposition, film deposition?
Interference between the filter and
the metal contacts of
the metal
VCSEL,
contacts. Well, that's where we would use photolithography to cover those during deposition. And then when we strip the photolithography, the bond pads are exposed.
Okay. Thank you so much.
We've been doing that for about 15 years now.
Well experienced. Good luck.
All right. Okay. If there is no further questions, thanks, Scott, again for highlighting this interesting aspect of the LIDARs. And I suggest we move to the third talk, which is given by Grégory Pandraud, the VP of Research at Ommatidia LIDAR. Grégory, welcome to the EPIC meeting.
Sorry, hi. Yes, thanks for the introduction. I hope you can see the screen. Yeah, is it okay? Yes, my screen is.
Yes.
Yes. Okay. Very good.
Just do the full screen.
Yeah, full screen. Yeah. Okay. Thank you. So yeah, I think I have 6 minutes, right? So I might have to rush, but I would like to introduce to you today what we do in terms of LiDAR on chip. Actually, we are using a chip in our system, Photonic chip. But before that, I would like to introduce very briefly Ommatidia LiDAR. So we have been founded 4 years ago. We are active in we have two sites, actually, one in Netherlands, one in Spain. We are more than 20. We were 5 last year, just to give you an idea of the growth factor. And at the core of our technique is a PIC, right? And so far we have been focusing on 3 markets, I mean space, civil engineering, and metrology, mostly because our goal was actually to reach the market as soon as possible. So if you want more information about the product itself, I mean what you can do, please go to our website. So what I want to do here today is to come back to FMCW video, because I think it's the only way to implement LiDAR on chip. That's my understanding. I would try to introduce our architecture and give some examples and go beyond that. So try to look at scanning up, because I think that was addressed somehow by Leti. But in terms of channels, I mean, those channels, we need to go much beyond that. And then I will conclude. So briefly, because I'm limited by the time. So I think everyone knows what LiDAR is. I mean, to get distance measurements for points in space. This is the FMCW scheme for 1 point, actually. It's important. And what we need, what we typically do is on the emitter side. So we eliminate the scene. So that's the main goal of the laser beam. So eliminate the scene continuously. And we pick up part of the signal to mix it then with the information that comes back from the receiver. So that's the emission, and that's the receiver. And by doing that, and what we do actually, we currently mix both the receiver information and the source. And because of the information, the beating frequency shift, we are able to extract distance information. Now, there are some benefits in using this scheme. One of them is the fact that we use heterogeneous detection, so that means we are short noise limited. And this helps, for example, for applications where range or the accuracy in the range is important. And furthermore, the only information we get is actually the information from the source, right? So that's and therefore we are also extremely immune to interference. I mean, nothing else in the field will affect at least light-wise, will affect the measurements. The system allows them to get amplitude and phase simultaneously, and therefore being able to plot points specific position in space. And now, of course, the scheme that I'm showed here on the right works for 1 point. Now the challenge is to bring this to a next level and multiple points. Now, one added important point from the FMC review is that, at least for us, particular implementation, is that anything that moves in the scene will be measured, right? So any Doppler effect because of frequency shift, and there are ways to actually split delay and velocity. That's a very common thing done in radar. But for example, in our case, we're also able to access vibration or movement in the field, and that's the main important information from FSC review is that actually velocity, the scheme brings velocity into play, right? So I mean, these are pictures, they are not ours, but I mean, it's clear that distance can be provided. That's standard LiDAR. But on top of that, it's also clear that the bicycle in this case is actually moving. Now, what do we do in our case? So how do we implement this FMCW scheme in our chip? So we have at the core then a PIC. That's what I explained. Now, in our case, we couple the light back into the PIC thanks to some optical waveguides. So we design the waveguide in such a way we are efficiently coupling the light back into the chip, and we mix the information coming back from the source at the IQ receiver, and by doing so, we are able to access the amplitude and phase. Now, how does it work? I mean, there are some design showed previously by CEA, right? I mean, similarly, it's very similar. We split the light from the source into a number of channels. We are receiving from the scene, and we mix them coherently in the middle of the chip. So the problem in this case is that it's purely a passive platform, so it's made of silicon nitride. So that means that we have to push the light out of the system in order to read out the information, and this is done thanks to some optical gratings. Now the system once package looks like this, and we have only one input. It's the input coming from the laser, the reference laser that we plug into the chip. The light comes back from the scene from the side of the chip. Now, beside that, of course, we have an elimination. So that's the receiver part. We have the laser on the other side. To answer a question that was in the chat, in this case, we use very standard DBR lasers commercially available, at least for these current applications. However, as explained, we have to get the information out. So in this case, we plug in indium phosphide line array detector on top of the chip. This comes with its own electronics. And these signals actually sent to an FPGA that allows us then to generate a full 3D point cloud, and therefore brought us to develop, to this product that we are currently selling. So that's our Q1 unit. And this, with this we have been involved in some project in which we have to either scan trees, because it's important, so all scan eventually people. This is actually one of our latest employee here in the Netherlands. Now, so practical implementation. What can we do with this system? So I mentioned the two main aspects of the difference we use: so the accuracy in distance and the vibration, right? So the fact that any shift in the scene would be captured. So metrology, we started from there with space, and actually we demonstrated that we can actually measure efficiently down to actually 20 micron accuracy this kind of shape. So these shapes are actually antennas for space. They are deployed to send information down to the ground and collect the information back. However, they cannot be they're not solid anymore because they cannot fit in the launcher, so they have to be folded before launch and open in space. And of course, there is a need for monitoring the position of these antennas while they're pointing, but also the shape of the antenna. So in this project, we demonstrated then on the limited number of points, because that was not required to do much more points in this case. So it's 11 by 11 matrix, an accuracy of 120 micron. Vibrometry. So what do we do then? In our case, we have 128 points, and we mount them on a scanning unit, and we scan actually the field. But what happens is that at each position, we are then able to collect all the information, all the vibration information from a line, which translates into, in the case of the guitar, so in this case, so we are not scanning the strings, right? It's the back of the guitar. So it's the body of the guitar. This allows us then to be able to access the full model vibration of the guitar, and this can be applied, of course, to different systems. Musical instruments are easy because they are very well-known frequencies, like 250, for example, which correspond to a Mi, I think, in the guitar. So in this case, it's the body of the guitar, not the front side that we are scanning. Now, this can be applied still in space for Airbus, where we look at the antennas. Similarly, instead of looking at the accuracy, we can also look at the movement of the antenna itself. So the system is actually very low, so they are moving very slowly, right? So it's more below 10 Hertz frequency, but you can really distinguish any of these peaks. And by the way, this was compared with standard accelerometers, which are also introducing some problems because they also modify somehow the vibration of the antenna. Now in the field, this can be applied. So this shows actually the current maximum distance we can achieve with the system. So by the way, it's a 40 milliwatt laser for information. So 40 milliwatts gives us already 80 meters distance. And what happens is that when the train, so we are facing high-speed train lines. When the train passes by, we can clearly see that before nothing happens, and then the trains significantly modify the vibration of the entire structure. And of course, the signal, this attenuates, of course, once the train has gone. One last example. So this is indoor. This is actually a bridge, and we are facing the bridge from the top. And here the idea was actually to compare with accelerometers. So instead of having, accelerometers, they need to be placed under the bridge. They are free. Well, actually, we can measure the full bridge actually at once with 128 points. And here there was a pretty nice correlation between what the accelerometers was giving and what we were measuring on that page. Now, so that's all fine. That's all nice. We are selling our product in these specific markets. However, we would like to go beyond that, and going beyond means scaling up in size and price, because so far the making the units, because of all these elements that we need to add, so detectors, the electronics, and others, makes the solution actually pretty expensive. So we got some help from the European Union. So we got a seal of excellence and the funding associated to develop a solution for automotive. We are aiming at agriculture, also being able to put our LiDAR on robots. We have kicked off last week a new project in which we were aiming at putting our LiDAR in drones And we have this financing with Korea, so Spanish-Korean financing that allows us actually to look at automotive. So, but then the thing is, what do we do next, right? So this is just in very short what needs to go. So this is the current solution that's mounted actually on a motor that allows us to build a nice point cloud, right? Dense point cloud. However, this is a very expensive piece and AV piece, by the way. We still have a single lasers, that's fine, we are not going to change it, but we have to keep in mind that single lasers, even in volume, is still $100. And we have to keep in mind that the price for an automotive LiDAR is $100, right? So it's not a problem yet, but it might become a problem. And of course, all these integration step needs to go. So I mean, the PIC plus the detector and the electronics should go. So we move towards what the CEA has been describing before. So we have moved to a silicon photonic platform. So still one point that we're going to plug onto an ASIC. So we are now programmed for the next TSMC shuttle. And we have developed also our own scanning unit. So all this should fit into a 10 by 10 system, so much compactor, but also probably much cheaper in price. At least that's what we believe. However, to go beyond that, of course, we need to be sure that the supply chain. I mean, so far it's fine, but I mean, supply chain can provide all the elements composing the system, the new system that we're going to put on market mid next year. However, to go even beyond, so the robotic applications and then aim at automotive, we need to definitely solve the problem of power, because we need, I mean, with the current source, we can do 80 meters, but we'll need to go to 300 meters, so meaning power times 5, typically. So, yeah, 500 milliwatts at least. And then we'll have also to start, of course, looking into reliability, so being able to produce a system, for example, in agriculture, where the environmental conditions are very important, so humidity, temperature are important, and slowly move to the automotive qualified products. So to conclude, we have decided to address first markets in which we can, I mean, where we believe FMCW-based LiDAR can be used efficiently, so mostly metrology, environmental metry for the high accuracy in depth and Doppler measurements in frequency. And the current efforts are now focusing on addressing scalability, meaning not do more than one, but mostly size and price to address market like automotive, infinite automotive. And I would like to thank you for listening to me. And if you have any question, please let me know.
Okay, thank you, Grégory. Quite a few interesting applications you covered. Do we have any questions in the audience? Please feel free to raise hands. Okay, Andrew from DeepLight.
Hello, thank you for the talk. How you achieve this micron resolution of your system with DBR diodes? How far you tune them?
The accuracy is actually given by the. Okay, so two things. It's an interferometric system, right? So that's already in itself accurate. However, we have also an heterodyne detection, right, which gives us actually a signal to noise ratio, which is pretty high. So accuracy is given by the signal to noise ratio. So in our system is pretty high. That allows them to get a pretty high accurate distance measurement.
Okay,
thanks.
Mm-hmm. Okay, then Eric from ST Micro, please.
Yes, thanks, Grégory, for your interesting presentation. So I understood that the road is still long towards automotive grade LiDAR, blah, blah, blah. But what is your feeling about the main roadblocks you will have to...
Yeah, so thanks, that's a good question. So chip-wise, I don't think we have too much problem. Integration-wise, I don't think we have too much problem. The key problem will be, as I said, at some point, the laser, because we have to keep in mind that the price at the end will be 100, 200, okay, 200 if we are optimistic. So, and nowadays, at least according to what I've seen, even at ACOC 2 weeks ago, a laser, even 200 milliwatt laser in volume is something like $50, $100 in volume. So that and the laser cannot be the price of the full unit, right? I mean, there are more elements in the system, even though silicon-based chip receiver is cheap. So to understanding, the getting power at low price might be a limitation.
But I was more speaking about, let's say, compactness and affordability is maybe second order, but is it still the lasers most important thing to miniaturize, or because I understood this is number one in your bill of material, but
yes.
If you want to reduce the size of your system, what is the first, let's say, important device?
What we are doing now is actually reducing the footprint of the LIDARs and the chip. That's what we do. And then after that, we have to get rid of the scanning system altogether.
Okay.
But I think that was mentioned also by CEA-Leti, but we are not going to move towards an OPA system for power consumption reason.
Okay, I hope that answers to you, Eric. So if there is no further question, I suggest we thank Grégory again for a very informative talk. And we move to the next one, which is given by Ward Wonder Tempel from VoxelSensors, the co-founder and CTO. Ward, whenever you're ready.
Let me share my screen. Good afternoon, everyone. Let's see if I can. Do you see my screen?
Yes, good to go.
Okay, so my name is Ward van der Tempel. I'm CTO at VoxelSensors. VoxelSensors is still a small startup in Belgium. We founded in 2020. And our mission is to develop technology for spatial computing. So spatial computing is a name for the next technology that will add physical context, so the knowledge about our environment, into our technology platforms and our applications. And mixed reality platforms, which are being released today, are a very good example of how this physical context is used to enable new use cases and new experiences. The physical context itself is created by sensing of the 3D world around us, but also of the users perceiving the 3D world. So in order to enable this spatial computing, what we need is contextual sensing. Now, contextual sensing has been a long-standing topic for a while. It is used in a variety of domains in mobile world, extended reality, but also robotics and automotive, for functions such as SLAM and odometry, for object identification, tracking, for semantic segmentation, etc. So there's a variety of applications which run today on this contextual sensing as an input of the data. However, if we look at the different requirements which are needed, for example, for augmented reality, which are, I've listed them here: power efficiency, latency, accuracy, and robustness. We see that today's technologies actually still have many limitations in trying to offer the right specifications of all these four requirements together. If we talk about power efficiency, also in augmented reality devices which are wearable, power efficiency of the sensing side is very important. So we need to reduce the power consumption of the sensing technology, while together with the low power, these sensing technologies need to offer low latency. And by low latency, I mean that there is no visible or perceivable lag between what's happening in the real world and the digital data which is being sensed of the real world. And together with the low power and the low latency, we still need the right accuracy in order to run our applications. And we want these systems, or sensing systems, to be robust and durable in a wide variety of environments. And if we put these requirements together, there is today's technologies are struggling to offer the right solution for many of these platforms. And so VoxelSensors set out to build a new type of 3D sensing or contextual sensing, and we are targeting this solution on two fronts. The first front is the sensing itself, where we developed a system which offers low power and low latency. And the second side is the computation. So what needs to happen with the 3D data being created. So we are also working on providing low power, low latency processing and compute. So this slide gives a very simple representation of the system that we have developed. It is actually a scanning triangulation system. It starts with a laser beam scanner, similar to the ones shown before in the context of automotive LiDAR. In this case, it's a single dot which is being scanned on the scene. The example here is a Lissajous figure, which you can typically achieve by using a MEMS-based scanner. Also, raster scanner or OPAs could be used for providing this part of the system. The point is that you want to send a dot towards a scene and scan the scene with this dot in a very fast way. And what VoxelSensors developed is a specific new type of sensor, which is capable of tracking the position of the dot in the image plane with a very minimal amount of power, so very low optical power which is needed. And we're using single photon sensitive imaging, so single photon imaging arrays for that purpose. And together with this very high sensitivity, the sensors need to also output information at very high speeds. So in this case, we are able to sample the position of the beam in the image plane with a temporal resolution up to 10 nanoseconds, so that is 100 megasamples per second. The sensor then outputs this information as serial way, so X, Y, T information. For every timestamp, there is one or more possible positions of the dot in the image plane. And this serial information is combined then with the knowledge of the laser beam projector, which is also a serial information of where the projection vector is at a given moment. And these two information streams, they can easily be combined to produce a triangulated point, a world coordinate point, XYZT, and provide a serial stream of 3D point information. The benefit is that we are sending one point at a time, so the optical energy is confined in space and in time. So in terms of fighting ambient light and other aggressors, this is the best case. And the sensors make sure that we can provide the right density of sampling in the right time by being very sensitive and very fast. The output of this system is then a serialized XYZ stream. And the nice thing is about this serialized information that you can look at it in different ways. And depending on the needs of your application, you could look at it with very short temporal glasses, let's say, and aggregate very little data, which will amount in very fast update rates of the sampling of your scene with a lower density, such as here, which can be very beneficial for tracking larger objects or for odometry, for example, when you have bigger surfaces to track. On the other hand, the same XYZT serial stream you can look at with a different aggregation window and accumulate more time and more data to provide a higher density at the cost of a slightly longer exposure time or aggregation time. Next to that, since I'm serially scanning the scene, I can also choose where and when to put power and when and where to sample. So for example, there is a simulated dot pattern here, for example, where I choose to send bursts of optical energy at specific locations in the projection field to mimic a kind of structured light pattern and provide a dot pattern, a sparse sampling in the scene. And in this way, I save a lot of power because I only allocate optical power and only sense with my sensor when I am actually sending out optical energy. On the other hand, I could also provide the full density of the pattern where I choose to. And I can combine multiple modes. For example, I could have a region of interest, which I define, where I keep the full density and allocate a higher sampling rate, while the rest of the field of view, for example, I just keep the sparse sampling. So there's a lot of flexibility that is possible with the system just because of the serial nature of the sensing paradigm. Moreover, because the way that we are creating the data is pipelined, it's coming in serially as it is being generated. You can also change the computing paradigm. So this is an example slide. This is work done by an academic partner in the Vrije Universiteit Brussels. So what you see here on the left side is the point cloud being built up. It's coming in an XYZT format. In the middle, this is a traditional computing algorithm which waits until the point cloud is available to start processing the point cloud and start segmenting it, for example, in this application or in this example. And on the right-hand side, you see a progressive version of this algorithm, which already starts to work on a sparse version of the data as it comes in, already tries to segment it, and then uses this information to further refine the segmentation as more XYZT points come in. And in totality, the algorithm for segmentation will be run much faster, as it already can start working on the data as it comes available. So in this way, we are also rethinking the application level, so the higher level, let's say, of the functionality in order to take advantage of the serialized nature of the acquisition to further speed up the functionalities. So in terms of why we're presenting in this community, so VoxelSensors is really about the sensors, the sensing silicon, and the system itself. So going into the 3D acquisition and the reconstruction. We are working with different partners for the laser beam scanning side. So we're very open to collaborate with different laser beam scanning operandi, so methods, where our main focuses right now are targeting the right field of view with the right scan rates at the right cost and the right size. So if you have a good laser beam scanning technology, I would be very open to discuss with you. Moreover, we are sampling evaluation kits at the moment. So if you think this technology could be useful for your type of application, don't hesitate to reach out and figure out with us whether we could be of any value in your target applications. Thank you for listening.
All right, thank you, Ward. That's a very interesting approach you have there. Do we have any questions in the audience? Please feel free to raise your hands. In the meantime, maybe ask one. I'm wondering, Ward, what would be the most objective figure of merit, like to characterize your approach in the sense of how much faster it works than the regular, how much more sensitivity you get, or what are the good figures of merit?
I think a good figure of merit is very hard to define. What our figure of merit that we use in the context of augmented reality is the power latency product. So given a certain density that is required for your application, there is a power and latency product that you can define at which your application needs to run. Again, augmented reality, you have a feedback loop between what your eyes are seeing and what you expect to be doing, manipulating virtual objects, for example, which interact with the real scene. And this loop needs to be very minimal. And typically, if you try to do that with other technologies running at 30 FPS, you end up with much higher latencies than are desirable. So this product, for example, in the context of augmented reality, is important to us. I can imagine that in the automotive context, there are different figures of merit that can be applied. There was a slide earlier about the difficulty of bridging those blind zones. So the cocoon around the vehicle is still a very hard volume to tackle with LiDAR technologies. This technology that we have could be an excellent partnering technology, let's say, to LiDAR in order to cover these short ranges. Because of the triangulation nature, this technology excels really in the short to medium range. We're not competing with long range LiDARs, for example.
Okay, I see now.
Yep.
Anyone else? Okay, Olaf, please.
Yeah, Mike, I was just going to ask about the range there, Ward, because that's the problem with triangulation. It depends on the base that you have.
Yes, correct.
So what do you think is the longest application?
Well, in the context of, if you're talking about automotive, and I imagine a baseline of 1.5 meter or something, then I can see that we can design a system up to 20 meters with a realistic field of view. I think that would be more or less the operational field of this technology, several tens of meters.
Okay.
If you increase the field of view, then it would be either with more sensors or if you have specific applications in mind, we can discuss in more detail.
All right. Mikhail from Smart, please.
Yes. So apparently you're using silicon as a base material for your sensor.
Correct.
Which will give you a particular wavelength restriction in the lasers as well. Just as a thought experiment, would indium phosphide as a sensor work as well? And would that give you advantages or disadvantages that you see? Did you think about that?
Indium phosphide, I guess if we can make avalanche diodes in this material which work well, then it could be a possibility. Now, this is really what we're developing is really an imaging technology.
Yeah.
I think if we're talking about wavelengths around 1300, then there are also developments of germanium spats, silicon germanium spats, which are probably more suited for the scaling that we require to make really images with it.
Yeah.
No.
Yeah, it's interesting. Thank you for sharing this.
Welcome.
Yeah, indeed. Thanks again, Ward. If there is no further questions, I suggest we continue with the agenda. So our next speaker comes from the DeepLight, the company in Switzerland, and Andrey Voloshin, the co-founder and the chief product officer, will tell us about the frequency agile photonic integrated laser for coherent ranging.
Yeah. Hello. Thank you for introduction. Thank you for the session. It's an honor for me to present here. And I'm presenting DeepLight. We're developing hybrid integrated lasers based on silicon nitride and MEMS actuators. So here we are discussing LiDAR implementations on chip, and I will speak about FMCW LiDAR based on coherent detection, or in other words, detection of the laser frequency. This approach has a lot of pros. It allows to measure velocity. It has high sensitivity. It could be long range, up to several kilometers, and the crosstalk between different LiDAR units is minimal. But this technology requires narrow bandwidth lasers and high linearity of the chip. And I would be happy to discuss with Grégory and like other LiDAR companies how they tackle this problem of the chip linearity. Let's be specific about these requirements for the linearity of chip. Here you can see the simulation of the bit node signal when we do homodyne detection using FMCW LiDAR system with a target at 250 meters. And if we have a laser with 1% of nonlinearity, there is barely no bit node signal. The bit node has a very low signal to noise ratio, and it's hard to define it, almost impossible to use for distance ranging. In contrast, lasers with the linearity of 0.01% or 0.1% provide a clean bit node, which is easy to use. Here, the chirp range was 1 gigahertz and the sweep rate was 10 kilohertz. So good linearity of chirp is needed, and people usually use active linearization of lasers or pre-distortion of driving signal. At DeepLight, we are tackling this problem to develop high-performing lasers, which is easy to control, and bring them to the chip to combine the best of the world of free space lasers and fiber lasers and the best of the world of silicon photonics on one chip. And we are using 3 different technology bricks. First of all, we are using hybrid integration and semiconductor laser diodes. Also, we are using ultra-low silicon nitride to achieve spectral purity of our lasers. And our key feature is MEMS actuators, which we monolithically integrate with silicon nitride. It is the most mature technology here. We are using the same processes which are used in our cell phones for filters, and we could fabricate at the same foundries. So using MEMS actuators, we can achieve megahertz range of actuation in comparison, in contrast to micro heaters on silicon nitride. So using this technology bricks, we explore different laser architectures. So first of all, we have self-injection locking. We could develop extended distributed Bragg reflect lasers or external cavity lasers. All of these approaches are compatible with low cost Fabry-Perot laser diodes or gain chips. And all of them provide frequency agility or fast tunability. We call ability to chirp a laser within bandwidth of 10 megahertz by few gigahertz frequency agility. And self-injection locking provides extremely low noise for long-range LiDAR. ETBR is the most straightforward approach with robust operation similar to DBR diodes, and the CL laser provides wide wavelength tunability. And what is important, self-injection locking could work in the region of optical frequency comb, when an optical cavity generates optical sidebands separated by tens and hundreds of gigahertz. We could use them for special multiplexing. And using this approach, we demonstrated megapixel video rate of LiDAR system and achieved 2.8 megapixels per second with a LiDAR based on optical frequency comb. So what we have right now is prototypes in standard butterfly packages with standard pin out and just 2 additional pins for direct access to the laser frequency. So a user just applies some analog signal to MEMS actuator and sees the same signal in the optical frequency. We have first pilot projects with first customers, and we also can offer custom projects to develop additional functionality on the chip, further linearization, delay lines, or coherent detection. And to be specific, let's take a look at the performance of our lasers. So here you can see the tuning curves of our laser when we just apply electric analog signal to our MEMS actuator. So the laser follows the analog signal. The chirp range could be 1 to 3 gigahertz, and the sweep rate is 1 or 100 kilohertz. And the nonlinearity is 0.1, 0.2%, and mainly caused by turning points, which doesn't affect the detection in the FMCW approach. And this is without any additional linearization of this laser. And this laser chirp signal is ideal for FMCW application. Basically, that's like how our lasers works. We have a lot of publications behind it. Feel free to contact me to request like more data or follow us on LinkedIn to learn more about our laser approach. Thank you.
All right, thank you, Andrew. That's a very impressive performance you showed. Do we have any questions in the audience? Let me start with asking you, in what quantities are those lasers available now?
So right now you see the standard butterfly. So we optimized our approach And right now we can fabricate like tens of them, let's say so, per month. And next year, our production volume will be 1,000 lasers per year. And we like the challenge for us as for startup to keep this volume.
Okay, that's good. Word from VoxelSensors, please.
Maybe a not related question, but can this frequency tuning also be used for beam steering in a certain way?
Yes, because for example, if we're talking about external cavity laser, we can have wide wavelength tunability. And in this case, we beam steer with change of wavelengths.
Have you tried that before?
Yes, we tried it. So we have, for example, one chirp for like small, one chirp for FMCW, and with micro heater we tune it over 100 gigahertz. And in this case, it's literally changes the direction laser beam.
Would be interesting to discuss further possibilities. Yeah.
Okay, yeah.
Thanks.
Putting you in contact. Eric from ST Micro, please.
Yes, maybe just a small, stupid question, but is there any kind of artificial intelligence in your device? Because your company is named DeepLight.ai.
That's historical reasons, and so far, no artificial intelligence. But in reality, when we package our lasers, we have like some optimization of alignment, and we could call it like AI. But in reality, we are just like Photonics hardware company.
Okay, thanks.
Okay, interesting. Good question. All right. If there is no further questions, I suggest we catch up with the agenda. Thanks, Andrew, again. So our next speaker is Raul Bravo, the president and the founder of Outsight. Raul, are you with us? Okay. Okay. Can you unmute because we don't hear you? Yeah. We still don't hear you, even though you are unmuted. No, we still don't hear you. Maybe, yeah, check the microphone settings in the Zoom. If you go on the bottom left of your screen.
Just changing.
Yeah, now it's good.
Now it's okay?
Yeah, go ahead.
Okay, great. So let's change a little bit after your impressive hardware presentations. We're going to talk about software and how LiDAR it can be used for different applications and how it's already been used, in fact. So this is what Outsight is about using LiDAR technology to track the movement of people and vehicles. And we're going to deep a little bit deeper on how we do that. First, perhaps just to provide an overview of who we are. So we have been spending a lot of years in 3D and LiDAR processing software. And have, of course, a lot of recognitions, awards, and many patents filed. 100 people in both France, Paris, and San Francisco, and with commercial offices in different countries all around the world. And all our customers, these are some of them, are using our technologies also in different parts of the world or in all continents. And the key message here is that these LiDAR software solutions are being applied to many different contexts and many different situations. So here we're going to focus in provide you some examples. Okay, so why LiDAR? Why our software is relying on this technology is because we are really convinced, it's not just a matter of faith, is that we are living this every day with customers, is that this technology has a set of unique capabilities and benefits that we cannot find in other sensors. So these are some examples, some key points, including the centimeter accuracy or even higher in some cases, but also, of course, as you all know, the ability to work in any lighting conditions and able to cover large areas. We're going to go deeper on that. And the privacy concerns are really increasing. So we are deploying these technologies in public spaces where the impossibility of identifying someone is something that is highly appreciated by customers. So there are many benefits around LiDAR. You all know that, but something that has changed in the last years, I would say, last 2 years, more or less. As I said in the beginning, we have been in this market forever, I would say. But what we have seen in the last time is that today, the technology is in a sweet spot of high performance, millions of points per second, and low cost. This is already the case. You can find a very competitive LiDAR in devices. And this is even more important if you take into account, as we are going to see in a bit, that the coverage per LiDAR is much higher than cameras. So the total cost of ownership for the same, let's say, surface to be covered is much lower with LiDAR. So the cost is not only a matter of per device comparison, but anyway, the key point here is that we are now in a sweet spot where this technology can be applied to many different markets beyond automotive, or I would say before automotive. And this is starting to be an unanimous opinion that all the other markets and verticals outside automotive are going to represent a very significant opportunity and market. And this is what we are seeing every day. So that's happening today. Automotive is going to come, but it's not today, and the other applications are already deploying. And I'm not getting into all the details of this slide, but if ever you want, we have written a white paper on that. But just keep in mind that even if the cost, of course, can be improved and is going to be improved, all the other metrics in applications such as people counting applications, you can see already that the comparison with other technologies is really positive. So we can do things that you cannot do with cameras and radars. So that's very important. It's happening today. Just to give you an example of what we are saying. This is a typical queue in an airport, for example, check-in security zone. You can see the people here, etc. And if you want to cover that, in the typical technology used in airports are cameras on the roof, on top of the seat of the context of the scene, and you can see in some airports, if you raise your head, you're going to see so many cameras installed there. And how many LiDARs would you need for the same situation? This is not theoretical, of course. For the slides, it's just a drawing, but it's a real customer case. If you use 360 LiDARs, you would need 4 of them instead of, I don't know, 5 times 6, some 30 of them. So this is what I was saying about the total cost of ownership for a certain surface. But even if you were using 2 good LiDARs, even front facing, if the ceiling height was not so high, then you can do with as little as 2 LiDARs. So you can see that the cost of LiDAR, it's a very relative subject when you go into the details of the context and the customer needs. And just to be even more precise, is one of the advantage of the LiDAR, of course, is this coverage, but the complexity comes from the diversity of solutions that you can find. As you all know, there are different ways of scanning a certain field of view, the typical 360 field of view, where you are covering all around the sensor, but because of the energy budget, let's say, you are not necessarily able to provide the same high range or long range for all the azimuths. And if you're using a front-facing, typical of automotive or other applications, of course, you're going to be longer range because you can focus the energy, and in some cases, you can get to longer range. But of course, you are missing part of the field of view, and any combination that you can imagine exists. So the key message here is that there is no one version or model that is better than the other. It doesn't make sense to put it in that way. It depends on the application. It depends on your needs, and it depends even in the specifics of the place or the premises where you are installing these sensors. So that's why we developed a 3D LiDAR simulator that is able to take into account all these specific capabilities and features of each sensor in order to provide the best solution for customers, the best combination of LiDARs, and the best positioning, orientation, etc., etc. And why I'm talking about that in our software is because this is all about our mission, is transforming complexity. We saw that there is already complexity in understanding which LiDAR to use, where to use them, etc. But it's even further than that, is that if you look at the raw data, of course, this is useless. It's needed, but it's useless per se. So you need to transform this data in something usable. And this is what we are doing in real time. We are transforming this raw data into actionable information. That means not only tracking people and vehicles, etc., but also calculating in real time key performance indicators. Just give you an example. In the case of people tracking and crowd monitoring, we are delivering key analytics that can directly be used in a dashboard or in any API connected system to manage your premises operations, safety, and security. This is what we are doing thanks to the fusion of different kinds of models and sensors. We are compatible with more than 95% of the market. All relevant LiDAR models and brands we are compatible with. And our software, it's fusing, combining the information of these LiDARs. In some cases, that means hundreds of them. So you can see that we are in a very different situation than compared to automotive, where you may have 4, 5, 6 LiDARs or whatever. Here we can have hundreds and thousands in some cases. So the kind of problems you're having are different. It's massive amounts of data that need to be processed. They need to be calibrated. They need to be synchronized, etc., etc. And this is exactly what we are doing. What you are seeing in the screen is an example of an airport terminal where each individual person and luggage is being tracked with a unique ID, which is what is the fundamental information that is informing the KPI engine that is delivering what I showed you before. So that's why we are doing in a context where when you are operating an airport or a train station or whatever, you may want to have these KPIs both as an immediate alert that is triggered because some threshold has been achieved. For example, too many people in a certain place, or the waiting time, it's longer than the maximum accepted, etc., etc. Or you may want to analyze the data over long periods of time. In some cases can be months, years, etc. This you can do it also with the same data. Of course, we show some examples of airports, etc., but the same technology it's being applied to any place, in fact, where the customer, the operator, can have an interest or can find a value or a security or safety interest in understanding how people are moving, how are they interacting to each other, etc., etc. The same exact technology is being used, that we are using it in vehicle monitoring applications. For example, in these examples, one of these examples, we are monitoring a intersection where the customer wants to detect near misses scenarios. That means situations when the car and a pedestrian or a bicycle are getting very close to an accident situation. So, of course, if you are detecting a lot of near misses, that means that you need to take action. Otherwise, it's going to become an accident sooner or later. So that's our quick overview of what we are doing. It's in a few words, we are making 3D spatial intelligence usable and affordable for many or almost any application that can have interest in people or vehicle flow monitoring. This is thanks to the hardware becoming more and more affordable and more performant. And Outsight, it's the leader and pioneer in this software processing field of 3D LiDAR. So I hope it was interesting and clear. If you want to know more, you can take a look at our website. And of course, you can contact us directly. And I will be happy to answer any questions you may have.
All right. Thank you, Raul. That was a very interesting presentation. There was a lot of interesting videos we could see from various applications. So now let's go into the questions. Eric from ST Micro, please.
Yes, hi, Raul. Interesting talk. You mentioned during your presentation several times airport or train station as let's say interesting applications, and you mentioned also security. But don't you think that the anonymous information you are collecting is somewhere contradictory with security needs, where you need probably at least face recognition or to really track the people?
Yes and no. It depends on what is your objective. In 90% of the security use cases, you don't need to understand who is the person or having Face ID. What you want is, for example, to detect an intrusion and being very accurate in where the intrusion is happening, where is the intruder now, etc., etc. If you need to identify the person, then
when you need camera.
Then we did exactly. We did. We demonstrated with Genetec, which is one of the main video management solution providers, that you can very easily match with a camera. So
yes, but if you have several cameras, one can think of using them to make stereo imaging and then reconstruct.
Yeah. In theory, everything is possible. In theory. In reality, we are working with customers that have felt real problems, and it's not easy, or it's not so obvious to create or obtain the 3D position of people accurately without LiDAR. Then you don't always need 3D intruder position. You can have a lot of use cases in security when you don't really need the 3D precision solution. But as soon as you need the 3D, or you have value in having the 3D with low false positives, etc., then LiDAR has a very, very specific value on that. Yeah. But you agree? I agree with you. As soon as you want to identify someone,
yes, for sure,
you need to use a non-anonymous sensor like a camera.
And I'm afraid it will be more and more the case.
It's not what we are seeing. What we are seeing is that there is a big interest in detecting dangerous situations, etc. And that is not necessarily needing to identify each of the individuals being involved.
Okay. Thanks.
Interesting. Second question from Andrew, DeepLight.
Thanks for nice talk. I'm a big fan of application of LiDAR for smart cities. I think it's a big potential. And have you tried to use this technology in combination with distributed fiber optic sensing when we're talking about perimeters? So we're working with these companies and like speaking about like intruders at railways, people really detect it with fiber sensing now. So are they somehow connected in your company?
I mean, for our customers are not necessarily the end user. Our customers are integrators and solution providers of technologies for smart cities, ITS, in that case, and they can perfectly combine our LiDAR solution with other solutions. So in some cases, it's exactly the same situation as the camera. In some cases, the combination of both is a winning solution. In other cases, you don't need the second one because you understand that LiDAR enough can fill your needs. It depends really on the context. So it's, and for example, if I get back to the camera based, you may still want to use a camera, but you may use a PTZ camera that is very slow in the movement. So because the LiDAR is the one making the tracking, then the PTZ can go straight to the point or to the azimuth, let's say, where the target is, and then you combine the best of the two worlds. That's an example. But this is not our company mission. It's not to do combination of sensors, etc. It's making the best out of LiDAR. And then depending on the context, our customers that are integrators or technological companies, they can eventually combine the data with other technologies.
Thanks.
Okay, that's a great mission you have there, Raul. If there is no further questions, yeah, I don't think there's one in the chat. There's no further questions. Yeah, let's thank Raul again, and we'll move to the last presentation of today, given by Chris Maloney, the Managing Director for the US operations and for business development at VPI Photonics.
Yeah, thanks, Ivan. And yeah, this has been a very interesting technology meeting so far. So I'm learning a lot. I'm looking forward to following up with a few folks afterwards. But yeah, what I'm going to talk about a bit is system-aware photonic integrated circuit design for LiDAR systems. So at VPI Photonics, just to give you a little bit of an overview first, our mission is really to empower you to define the cutting edge. So we provide simulation software tools for you. And so we've been in business for over 25 years. As Ivan mentioned, I run our US operation out of Rochester, New York, and our headquarters is actually in Berlin, Germany. And the way that we like to describe our software is using these three terms you see here. So it's integrated, meaning whenever we develop a new software tool, we want to make sure that our different tools actually are integrated together. Many times they're in the same user interface, so it's very easy to go between one and another. They're also interoperable. So if you're used to doing Python or MATLAB scripting, it's very easy to bring your custom modeling or simulation tools directly into the software. And we also claim to be industry leading. So we're always working with partners. A few of you in the room, we're on common projects together, and we're taking what we learn from those R&D projects and building them into the software. So LiDAR has actually been a bit of a focus for us over the past 2 years. So we brought some new functionalities into the software. The main thing I'll be focusing on today, though, is how our software tools are actually integrated together and how those can be used to design a LiDAR system. So I'm going to talk about our flagship product, VPI Photonics Design Suite, which actually includes a number of different tools together in one user interface, one design environment. And so I'll be talking both about the transmission design layer or more system level simulations using VPI Transmission Maker optical systems. and some of our component design tools, one specifically VPI component maker Photonic Circuits, and how those can be actually used together. And one thing just to point out, we do also support PDKs at various photonics foundries. So if you're using some of those, indium phosphide lasers, you might go to some of the foundries. Actually, I see Smart Photonics in the room. That's one of our partners. Or there's some silicon nitride foundries that we support as well. So we can actually bring those models from those foundries into the software and run some simulations. We also have other tools at the device level and network level, but that's kind of beyond the scope here today. So first, just getting into VPI transmission maker optical systems. This tool is really used heavily in the datacom telecom industry, but there are a lot of parallels between those working in that space and those in LiDAR, as really, like an FMCW LiDAR system is really very similar to an optical transceiver used by datacom companies. So you actually see a number of those businesses having R&D groups kind of working in this space as well. But this tool covers a lot of different applications, from short reach to long haul fiber systems. And more recently, we've gotten into taking the tools that we have and extending those tools to be useful for free space optical applications like satellite communications, but also LiDAR. And so you can see we have, schematic-based design tools. We have all types of transmitters for different modulation formats. We have models for free space optical channel model, including atmospheric conditions, which I'll talk a little bit about today. And then also receivers. So balanced photo detection, digital signal processing, we can leverage all the tools that we have for designing LiDAR systems as well. And those are more, behavioral level models, but we can actually get into more physical level modeling using VPI component maker Photonic Circuits. So we have models for active components. So I know you heard a little bit today about DFB, DBR lasers. We have models for those, SOAs, passive components. So I know those optical phased arrays that were mentioned previously are made up of a number of MMIs, Mach-Sender modulators if it's needed. And so we can start to put those components together and connect them together in a circuit for different functionalities. So you can see an example in the lower right corner of a widely tunable hybrid 3.5 silicon laser. So you can see there's some ring resonator sections that can be used to tune your laser. So maybe those are made out of silicon or silicon nitride. And there's an SOA that's combined with that. So maybe that's an indium phosphide SOA. So we can combine those different material platforms together to create and simulate a chip. You can perform different sensitivity analyses, investigate fabrication tolerances at the foundries. So you know more about what you might get out of your PIC through your simulation before having something fabricated. So those are the two tools that we're going to talk a little bit about today and how they can be used to help design PICs for LiDAR systems. So I have to thank Grégory a little bit because he already spoke about a system that's very similar to what I have prepared here for an example for designing an FMCW LiDAR system. So I'm just going to walk you through some of the components here that we have in this more system level model. So on the left side, you have your transmitter, which is made up of a driving signal, CW laser. And in this case, it's an idealized system, but one thing that we are including is a non-zero line width to that laser. We do some frequency modulation. The signals then split both into a probe and a reference signal. And then the probe signal passes through a circulator and then passes through our free space optical channel model. So in this, we can account for things like different weather conditions, so how that impacts the attenuation. Maybe you have a heavy fog, rain, snow. So that can be taken into account. And then we have our target, which is a pretty idealized emulation of a target where we do a frequency modulation if that target's moving. So then you can start to see how velocity of the target will impact your detection. And then the signal is brought back through free space again, back through the circulator, and it's combined for balanced photo detection with the reference signal. And then we can do some detection of, let's say, where the beating frequency might land. So you can see an example here in the lower left, your electrical driving signal. So it's this triangular waveform, fairly idealized. And then the optical signal of your probe and your reference. So then you can see this shift and between the transmitted and the received signal, and that's where we can get our electrical spectrum and actually detect the distance to the object. And if the object's moving and there's a frequency shift, there's a Doppler effect, you'll actually get 2 of those peaks, and then you can start to measure velocity. So that's the system level approach. It's good to have that, because then you can go and dive a little deeper. And let's say you have a photonic integrated circuit based transmitter. And so, Andrey, you actually already introduced this, the concept I'm going to talk about a little bit, and that's the nonlinearities from your laser. And so it's one thing just to say, okay, here's the nonlinearity of the laser, but it's another thing to say and simulate, how does that actually impact your detection performance? So what we have here on the left side is actually a DBR laser. So now you can start to see some of our PIC components. And so now there's some more impairments that can be included here. So these are bidirectional models. So we have these grading mirrors, we have a phase tuning section and a gain section. And using our Photonics TLM model, this transmission line laser model, we can include things like, let's say, back reflections into the laser cavity. How's that impact the laser? Or spatial hole burning or Kerr nonlinearity. So it's a pretty sophisticated model, but also it's a circuit level model. So it's actually fairly quick to simulate. So you might think of this as taking a few seconds or a few minutes, as opposed to a more device level model, maybe an FDTD simulation, which could take hours or days. So we're trying to take a more efficient approach to this. So now if we include this PIC design in our system level simulation, we can start to see our electrical driving signal. It's pretty linear, this triangular waveform, and we can simulate how that impacts the nonlinearity of the signal after passing through this or output from the laser. So you can see there's some nonlinearity here. And actually, Andrey actually showed a very similar result in his experiments. You can see how the detection performance will degrade because you're not able to have that resolution in your detection of that beating frequency. So now adding these PIC components, we can start to see how these nonlinearities would impact a system. And so one method for compensating for that is to provide some pre-distortion to the signal. So now the driving signal, you can see, already has some distortion to it that we're pre-distorting our system with, and we can compensate for that nonlinearity and bring back the integrity of our signal. So that's just one thing you can start to explore with this type of software, but it is important both to include your PIC design and your more detailed physical modeling of your PIC, and see how does that actually impact the overall system performance. So it's important to look at things from both perspectives. So that's just one taste of what we can do with our software. We also have examples for optical phased arrays and exploring the performance of that as well. So not just the detection, but the range, not just the ranging, but the beam steering applications as well. So this integrated design workflow really allows you to explore a lot of different things. And as you can get into it, you can see it can get more and more complicated. So what we want is to work with more and more of those in the industry, to work with partners, to bring new application examples into the software, to build upon these concepts. So feel free to reach out. You can see my email there. Also, if you're interested in a demo or a software evaluation, please get in touch with us. We're happy to support that.
Great. Thank you, Chris. great presentation and a very flexible solution of VPI photonics right there. Do we have any questions in the audience? Have you already tried the VPI solutions? Okay, Andrew, DeepLight?
Yeah, it's like a headache. This non-linearities, how to simulate the system. This is very, very nice tool set and like, looks very good. I have a question. So we are working with this thing called self-injection locking. It's like pretty old concept of lasers, but not so like well established. So do you cover this thing in your simulation toolkit?
So we do. I believe we have some examples in the software already, because it's a fairly known concept. But I think the applications that we have them in the software for are more datacom, telecom centric, but it should be pretty straightforward to apply them to this use case as well.
Thanks. Let's talk later.
Yeah.
Yeah, I'll make sure to put you guys in contact. Okay, anyone else? All right. Well, if this, I guess everybody's tired already, but yeah, thank you very much, Chris. This was a very interesting solution that you offer. So yeah, please feel free to follow up to Chris and to all the other speakers of today's session after the meeting. Also, you're welcome to stay in the room for a little bit longer for the, let's say, off-the-record discussions. Let me just share a couple of things with you before the end of the meeting. So this was the online technology meeting on LIDARs on chips for you, presented by EPIC, the European Photonic Industry Consortium. Right now you have the standard poll to give us some feedback about this meeting on your screen. So please give us your opinion. I want to thank again all the speakers of today's session. So Frédéric, Thierry, Scott, Grégory, Ward, Andrew, Raul, and Chris. So thanks again. That was great to hear your vision of the LIDARs on chips and what photonics can do for it. Apart from this, keep in mind that we continue the series of the online technology meetings. There is one upcoming on the optical design and simulations, one on the new mid-IR developments for novel industrial manufacturing, and another one for photonics on food and beverages. Apart from this, make sure that you follow the EPIC at our offline physical meetings. There is the upcoming meetings are devoted to laser applications for battery manufacturing, the microelectronics and photonics, and also a few TechWatch events that we have. Out of those, I want to really highlight this meeting that will take place on the 13th and 14th of November in Munich. This is the meeting that will cover both the microelectronic and photonics topics, and especially the overlap of the two. It takes place at the Messe Munich in parallel with the very large semiconductor exhibition, Semicon Europe. So you can hit both events in one shot. So please make sure you consider the program that we have published on the EPIC website, and you're welcome to join us. That's in 3 weeks from now. So with this, I'd like to also say that this event was provided to you by the whole team of EPIC. So I thank all my colleagues for helping out. And this was it. So thank you very much, and I hope you have a very good rest of the day. Thank you.